Hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So I am your tutor for the physics subject. So in the upcoming 3 classes, I will discuss that what we have learned so far and solving some problem related to that helps you to understand the better understanding to the subjects, and we will discuss some at the end. We will discuss some conceptual problems. Okay, so let's first do the summaries that what we have learned so far. So we first discuss the Coulomb law. Okay, so that means the electric force exerted by a charge q1. So electric force exerted by a charge q1, okay, on a second charge q2, on a second charge q2, so is given by Coulomb's law, right? So is given by Coulomb's law. Okay. So the Coulomb's law suggests that the force between charge 1 and charge 2, q1 and q2, so if 1 to vector, so this proportional to the amount of charges, so it is the proportionality constant k, Coulomb constant times q1 q2, and inversely proportional to the square of the distance. So r square if the distance between the q1 and q2 charge. So let us say this one is q1, this one is q2, and the distance between them is r. Okay, that is the r cap. So there is a direction r cap is the line joining between the two. Okay, the direction line joining between the two. So and where the constant k is called the Coulomb constant. Okay. So the value of this 1 over 4 pi epsilon naught, this is the permittivity of the free space. So is 8.99 times 10 to the power 9 Newton meter square per Coulomb square. Okay. So this is called the Coulomb constant. Coulomb constant. So now this force is a fundamental concept, but if you understand this, so there is an intermediate concept is called the electric field. So the second one is the electric field. So the electric field at a point in space, electric field at a point in space is defined by so this E vector, the limiting case, so limit q tends to 0. Okay. So let us say call the q naught, and this Fe vector divided by q naught, right. So this one basically says that if we consider a charge capital Q, right, and we consider another charge q naught, that is called the test charge. So you want to calculate the electric field at that point P, okay, where the q naught charge is placed due to this capital Q charge. Okay. So we first calculate the force between this by Coulomb's law, okay, and we divided by q naught. Now it turns to that there is a no q naught, so q naught turns to 0 limits. This basically gives the electric field E. So electric field is defined from the force. So it is important that the force is a fundamental thing. So we have to define by Coulomb. Force is written down by the Coulomb's law, and the electric field defined from that. Okay. So electric field is an intermediate concept. Okay. So you have to understand the whole pictures. Okay, how the force act on this second particle. So the intermediate concept is field. Okay, but electric field is defined from the force. Okay. So in this way, and the electric field at a distance r. So if there is a distance r. So now once we know the force Fe, so we just write down this, that Fe is 1 over 4 pi epsilon naught q by capital Q by r square, right, capital Q times q naught. So now divided by q naught, and in the limit q naught tends to 0. So the electric field at a distance r, so at a distance r is E vector capital Q over 4 pi epsilon naught r square, and the direction is the same as in the first direction, so r cap. So now we discuss the superposition principle. Okay. So the superposition principle basically tells you how to calculate the electric field due to a charge configuration, okay, a discrete charge configuration. So the superposition principle. So you have to consider a discrete charge configurations. Okay, so let us say you have considered a discrete charge configuration. Consider a discrete charge configuration. At ith point there is a charge called Qi. Okay. So this ith point from the origin. Okay. So if you consider x is x y, right, and you consider there is some charge configurations. So we labeled each point as I. So I means 1, 2, 3. So by notation we denoted by I, and located at a distance, let us say Ri from the origin, Qi, and located at a distance Ri. From origin OI, right. So the distance is Ri Qi. Now the electric field E, the net electric field, let us say at origin, the net electric field at origin, so denoted O, it's become 1 over 4 pi epsilon naught, so sum over Qi, the amount of charge, divided by Ri. So this Qi including the sign, okay, sum over I divided by Ri square and also Ri hat, right. So this is a unity vector in this direction. Now so Ri, these are the scalar quantity, but this one is a vector. So we add the vector sum, okay. So we will discuss in the class, okay, in great details, and we solve some problems. Okay. So now suppose there is a continuous charge distributions, okay, then we use a vector integral, okay. So we will come into this point. So then we calculate charged particle, the motions of a charged particle in an electric field E, right. So we say that if we consider a uniform electric field E, so uniform electric field E, so in a uniform electric field E, the particle of mass m and charge q have oscillations. The particle of mass m and charge q, right, have oscillation. So has an oscillation a vector q times e vector over m. Okay. So here we consider the uniform, but it may not be uniform. Okay. So any uniform electric field, so basically the a vector is f vector over m, right. So now we know that the f vector is q times e vector, right. So here e in any, so uniform or non-uniform, okay. So here we denote the in an electric field, okay. So in electric field, any type of electric field, okay. Then we will discuss the electric dipole, right. So electric dipole, so electric dipole. So this electric dipole basically consists of two equal and opposite charges, Okay, so that is remember. So when you consider a dipole, so the two charges must be same amount, plus q and minus q, right. So sign opposite, but the charge amount is same. Okay, so they create a dipole. So consist of two equal but opposite charges, two equal but charges, right. And the electric dipole vector in which directions? Negative charge to positive charge, right. So in these directions the dipole vector, so it opposite to the field direction, right. So field direction is that from plus q charge is pointing outwards and from minus q charge is pointing inwards, right. So the field direction is plus q to minus q, but the dipole moment vector is opposite to the field direction, so plus minus q to plus q. Okay. So this is the dipole moment vector, and the magnitude of this basically amount of charge q times the distance between them, let us call 2a. So 2a basically 2a q, this is the dipole moment, the magnitude of this. Now if we place this electric dipole in an uniform electric field E, so now we place an electric dipole, magnetic dipole and electric dipole places in a uniform electric field. So here is uniform is important. Okay, it depends on the if you consider the uniform electric field or not. So first we consider the uniform electric field E. Okay. So there on this dipole there is a torque. Okay. So the torque tau vector equals to p cross. So this is a vector product. So this is vector cross means the vector product. Cross product, other way to say. So since the electric dipole is placed in a uniform electric field, okay, so the only torque appears on the dipole, not force. So net force becomes 0. So if we place an electric dipole in a non-uniform electric field, then both torque and force are acting on the dipoles. Okay. So we will discuss and solving a problems, okay, related to that, and then become it's more clear. And then we discussed the potential energy. So the potential energy of an electric dipole in an external electric field. Potential energy of an electric dipole in a uniform external electric field A. So here we consider the uniform external electric field A is U minus P dot A. So we'll derive this formula in the class. So the minus sign is important, okay, since the potential energy. Okay. So the minus sign is important, and so okay. So now we are consider a continuous charge distributions and how to calculate the electric field. So the electric field at a point in space due to a continuous charge element. So I am just writing the formula, and we will use this formula, okay, and solve some problem later. Okay. So due to a continuous charge element dq is dE vector 1 over 4 pi epsilon naught dq over r square R cap, right. Okay. So now, so basically what is the difference between that for a continuous charge distribution and point charge distribution? So if we consider the point charge distributions, that means the charge distribution, discrete charge distributions, right. So then we use the superposition principle to calculate the electric field at some point due to all the charges. Now if we have a continuous charge distributions, okay, so then we have considered the first a small element, okay, and then we calculate the electric field at a particular point r, okay, due to the small element, and then we integrate. Okay. In the case of continuous charge distribution, the superposition principle basically replaced by the vector integral. So in this case we evaluate the vector integral, evaluate the vector integral. So this E vector 1 over 4 pi epsilon naught dq over r square r cap. So integrate over all the r. So here is the r is distance from the dq to r point. Okay. So basically the if you draw a diagram, so let us say we have a line charge distribution. So we have a line charge distributions, basically consider a rod L, and you first consider a small strip on the rod that charge as dq, and you calculate the field at a point r at a distance smaller from the point dq, right, from the small element dq, and then we integrate, because now the r is a continuous variable and dq is a continuous variable as well, right. So in the limit of q tends to 0, so dq tends to 0, sorry, in the limit of this length, okay, dx tends to 0, so we use a continuous variable and integrate, right. So in this case we must evaluate the vector integral for a continuous charge distribution. Okay. So it can be anything, any of the three distributions, okay, line, volume or surface charge density, and RKB in this direction, right. So RKB changes for a different elements. Okay. Okay, so in the next class we'll so in the next class, so in the next class we will consider the three types of charge distributions and how to solve the problem for a continuous charge distributions, okay, that we discussed already in the class, but we briefly recapitulate those things again. Okay, thank you.